Hey everyone, this is George Hedden, founder of PauseFest and Awards, and you tuned into the Breakthrough Sessions 2024. We're all about the clever ideas that push boundaries, and for the next couple of weeks left, we're bringing you some of the sharpest minds in the business to talk about what's happening right now. Every Friday from September 6th to October 25th at 1 p.m., we're live for 30 minutes, just enough time to give you some serious insights without pulling you away from your busy day. So let's dive in, get inspired, and most of all, let's break through together. Today's session is Joint AR. Discover new extravehicular activities. Explore how cutting edge augmented reality technology is transforming spacesuit design, enhancing astronaut decision making, and enabling safer and more efficient planetary explorations. I'm very excited, even just reading this. Our speakers, Sarosh Nandwani, human systems engineer at Johnson Space Center. Her main role is to analyze and test hardware and software human interfaces for any human in the space exploration loop, including ground and crew. In her free time, she loves to draw, read space fantasy, cosplay video games, and bake bread. Matt Noyes, mechanical and software engineer at NASA. His career has included insight in and oversight of future lunar rovers, next generation spacesuit, and development of augmented and virtual reality technology for the future Artemis missions and astronaut support, including acting as software lead or joint AR. That concludes my introductions. Thank you very much for joining us all the way from USA, Dallas. I sort of presume I'm a big fan. As you can see, I have a sort of I'm wearing some of the NASA stuff, and but I won't sort of take any more time. Please, yeah, let's just roll into it.
Okay, sounds good. Thanks for the introduction. And I just want to confirm you guys can still hear me okay and it's clear. Yeah, okay. Thanks for the thumbs up. And you can see my screen as art as well. Okay, sweet. And I'm in my window. Okay. So yeah, this is a presentation about joint AR as in augmented reality. Going to be talking a little bit about our joint AR team's journey in developing an augmented reality heads-up display for spacesuits with a particular and specific focus on navigation. So I'm Sarosh. I work as a human systems engineer at Johnson Space Center, and Matt Noyes is an aerospace technologist in the software engineering branch, and he'll be jumping in to speak a little bit about the software portion of this. So first, and this presentation will go through several aspects of the project. I'll talk a little bit about the team, and I'll also kind of walk through the design problem, how we came up with the solution, and then the solution itself, and how it is uh, has been proven through testing to help support efficient and effective extravehicular activity. And for those who don't know, extravehicular activity is just basically a spacewalk. So it's anytime crew is inside a full spacesuit, outside of whatever module they're in. And our project was specific to lunar extravehicular activities specifically. So walking on the lunar surface was our main use case. So now jumping into kind of the nitty gritty of the project itself. So first, I kind of want to cover like what are we looking at Johnson Space Center? What are we bringing together in order to do a project? So we've got three separate things. We have inspiration, which is just thinking about humanity, about culture, about STEM, and really, really building the world. The second is science. So looking at heliophysics, astrophysics, human research, planetary research, especially on the lunar surface. And as we make our way to Mars, we'll be thinking a lot about the science and where the planets came from, what kind of compounds exist on them, that kind of thing. And then third, we've got national posture. So that's more like forging international relationships, influencing the globe. And there's a ton of really great space agencies doing that work right now as well. And so those three things together kind of drive the economy, leadership, and human condition that we develop and exercise at Johnson Space Center. And on the left, this is actually a sneak peek of what the solution looks like. This is the joint augmented reality system. And we've got an astronaut here actually wearing the full system and using it during field testing. And I'll kind of talk through all of that as we go through this. I'm actually going to also look at the time and make sure I'm not going to go over. Okay. So the first question is, what does it mean to be autonomous? When we think about moving on eventually to Mars and actually operating there, potentially living there, astronauts and people who are there are going to have to operate autonomously. There's going to be an enormous communication delay if there's an emergency or a plan needs to change, or there's a surprisingly cool rock that an astronaut wants to go check out instead of sticking to like their plan. They won't be able to contact mission control and get a timely response. So when we ask, what does it mean to be autonomous? What that means is on Mars, all the astronauts are going to have their timelines. They're going to have to be able to plan and replan their timelines. They're going to have like live updating maps so that they know where they are. They're going to need to be able to communicate with each other really easily, see the same information, and have dynamically changing information so that they know how much more oxygen do I have left? Are there any health conditions I need to worry about? Are there any mission objectives that I'm missing? Because they won't be able to contact mission control. And this is just going to get more and more difficult as we go from the moon to Mars, from moon to Mars. So we're asking some questions then, right? We're asking questions like, what does the crew member need in order to make decisions? Right now, mission control makes the decisions. That's part of the entire flight operations landscape at Johnson Space Center and NASA in general. Astronauts right now are in low Earth orbit, and so it's a lot easier to be like, hey, help me out with this. What do I need to do here? So the question we're asking when we talk about navigation specifically as well is like, what kinds of things do you need on your display in order to do the things that you need to do? And it's a lot harder of a question when you think about lunar navigation because it's very different from pedestrian navigation. When you're on the lunar surface or the Martian surface, it's a completely featureless area. There's maybe some craters, there's maybe differences in height and elevation, but it's very different from navigating on Earth, where you have roads and signs and buildings that you can reference in order to get where you need to go. So, what do you need on your display to make decisions? What do you need on your display to know where you're going and where you are? What do you need on your display to be able to replan something? And what do you need on your display to work with somebody else to solve a problem? Those are the types of questions that we're asking when we think about how are we navigating on Mars? So this is kind of the like process by which we get to developing a project. So we start off with the use cases, right? And our main use case is conducting crew lunar surface extravehicular activities or lunar spacewalks. So basically, right, astronaut on lunar surface walking around. How the heck are they doing that? And then also providing a common data interface on the lunar surface. So not just crew walking on the moon, but everything on their display being accurate information, up-to-date information, clear information. That's the use case that we're looking at. How do we get them that information? How are they using it? Is it helpful to them? Does it interfere with their mission? From that use case, we can derive some requirements. So your system shall XYZ. And your system shall display this and be like this and use this amount of power. And that's where we get to innovation with a limited budget, of course, because this is a government agency. Don't have unlimited funds. And so working with smaller deadlines, a smaller budget, and driving something completely different that nobody at the agency has really done before was a huge, huge challenge for our team. And so this is kind of where, okay, this is the use case, the astronauts doing this thing, walking on the lunar surface. This is where we find some of the like requirements or things that they would need to see in order to navigate or just operate on the lunar surface. There's a variety of things that we were kind of working towards in the process of developing our joint AR team. So we were looking at, okay, how is crew going to annotate their photos and videos if they need to? Right now, the current system is that kind of like a disposable camera. If you take a picture, you don't really know what that picture looks like after you've taken it. Crew has no idea of like what the picture looks like. So being able to see their photos and videos, super important. Photo viewfinder, they can't even see what the camera sees. The camera is mounted somewhere else. So it's even harder than like a disposable camera. being able to see their consumables, so their oxygen levels, carbon dioxide levels, other things like that. Science tool interfacing, especially when they're doing things like geology. So if they're picking up a sample from the lunar or Martian surface, how how is their suit interacting with that? How are they tracking that? Their procedures, what do they need to do? Mission control updates. So if they're on the Martian surface and MCC wants to send them an update, how are they doing that? What does it look like? Crew messaging and mission control messaging. So can crew talk to each other via their display? Can they talk to MCC through like NIM? Monitoring their timeline, and that has huge impacts on decision making, navigation, as well as augmented reality graphics and cues. The main goal that our team focused on was primarily navigation. There's a few there's a few reasons for it, but the main reason is that during field testing, it was found that in a featureless environment where there's not a lot of landmarks to go off of, crew have to spend a lot of time just looking at their map. Like they have to spend, it was about approximately 20% of their time and energy and words just trying to read the map, figure out where they are, where they're facing, where they're trying to go. And so a lot of the solutions we came up with were mainly focused on navigation, because again, limited budget, limited time. We wanted to focus on a high priority ticket item. And then we were looking into, right, what's the best way for crew to have all the information I mentioned on the previous slide, and in particular for our project navigation. And so AR technology is kind of where we thought the most benefit would happen. So easy access to information, it's just in your field of view at all times. There's multiple control modes that are possible. So you could use voice, gestures, a physical controller. You can overlay your information with the environment. So you don't have to detract, right, from, and for those of you in AR industry, you know this, you don't have to detract from the task that you're doing because all the information is overlaid onto what you're doing. Hands-free ability to perform tasks. This was a really, really big one. So when crew is doing geology sampling, doing any other procedural activities, using robotics or whatever the case is on the lunar or Martian surface, they need both hands generally. It's really difficult to do things with just one pressurized gloved hand. And so having a augmented reality display, for example, with navigation, means that they can just keep walking. They can see where they are, where they're going, and they can just keep walking instead of needing to potentially bring out a tablet or bring out like a smaller phone form factor, look at it, distract from the environment, look at that, and then try to navigate that way. So yeah, minimal impact to operations. There's also the possibility of having things in your physical environment. So thinking like in video games, when you see like a dot on the floor that you're trying to get to, that kind of thing. One of the really important and critical things that I think helped our team develop something innovative, something game changing, and something helpful for crew was working in the same room. So, not the same building, not the same hallway, in one lab space. So, we had hardware, software, avionics, human factors, testing and operations, and user experience all in the same room. Every single time we were working on this, we were working off of pretty much the same prototype. And that was really helpful because we could rapidly take a look at things that would usually probably take a bit longer to get through. It was also easier because we didn't have multiple versions of something. So that I think that was like a really, really big strength of how we got to the main project and where we ended up. Time check. So this is kind of, yeah, sneak peek of what it looks like. So on the left, you saw this earlier. This is the form factor. It's kind of a piece of glass, like half a pair of glasses. And there's a waveguide projector on the side. You can see my mouse, it's right here. And the waveguide bounces light back and forth in order to project it onto the glass display so that the user can actually see it.
So
And in the
Rosh,
top,
I'm
yes.
sorry, but we don't see the presentation in case you're presenting.
Oh gosh,
We haven't seen anything yet.
you haven't seen anything at all?
No,
Oh, that's really embarrassing.
I've been
I
seeing this.
actually,
you
I've been,
have. Okay. I'm not seeing anything, but if you guys seeing it, that's great.
Okay, so on this screen, you should see on the left, there's a person wearing the system, and on the right, there's two displays. Can someone confirm that they can see it? Just wanna make sure.
I see that.
The
Yep.
sides. Okay, I see the chat. Okay, thank you. Um, okay, yeah. So this is kind of what the options look like on the right, and what we tested with for the AR UI display. And I'll go through a little bit more of exactly what's on there. But first, this is a video, and I hope the video actually updates. Someone can let me know if it doesn't, but you can see, right? Matt was actually the one that videotaped this. You get like a really good view of what the person is looking at inside of their lens. So in this, you can see, right, you've got your dot, you've got a heading cone, and that kind of in this full setup is demonstrating in field testing how augmented realities for a spacesuit is useful for testing. Oops. Okay. So this is NASA astronaut Andre Douglas. He was wearing our joint AR display technology during field testing in Arizona. So I explained a little bit about how that technology works. I do want to note here as well that one of the things that was challenging is that the vision, the like ultimate vision for this was an augmented reality display on a helmet bubble. And if you're familiar with a spacesuit helmet bubble, it's a curve. Um, the technology a few years ago when this project started was less advanced than it is now in augmented reality. And even today, I'm not aware of any technology that can display content onto a curved surface. I just want to make a note here that our team, despite that technological limitation, believed in the vision and believed in the innovation of that technology eventually enough to test the operations using a mock-up. Now, I believe I will turn it over to Matt to talk a little bit about the software.
Thank you. Can you hear me with clear audio?
Yes.
Yes. Okay. So I'm Matthew Noyes. I was the software lead on the Joint AR project. And here I'm going to talk kind of the story of how we went from trying to use commercial engines for graphics to creating our own graphics engine to support the development of our displays. So when we initially started the project, we were kind of given the task at the very beginning to choose from a wide variety of user interface frameworks. And we did a trade study for that based on engines that were commonly used at NASA and other common graphics frameworks. So the idea of a graphics engine is that you simplify all of the low-level computing programming commands necessary to create pixels on the screen so that a developer only has to say, I want to draw text at a specific position on the screen. I'm not going to worry about setting up swap buffers or texture maps or anything like that. It's all going to be handled by the software. So we had a pretty good mix of people involved in the decision. We used a decision matrix to try to create a quantitative decision-making process that we could go back and do lessons learned from on whether or not we chose wisely. We had a mixture of senior advisor, kind of subject matter experts that have been around for a long time, have real world industry experience. But we also had what we call the naive experts, the people that are just out of school, so they're more familiar with kind of the state of the art. But at the same time, they're also not limited in the scope of what they believe is capable, of what they believe technology is capable of, because they kind of don't know what they don't know. And I think of the engines that we picked at the time, we picked a pretty good one. Probably the best, I think the best option that we had at the time. But as we started working with it, we found that there were some kind of deficiencies, not only in the feature set that we needed, but it was also just overcomplicated. Basically, because we're developing flight software that could be potentially safety critical, especially when we're dealing with navigation issues, we have to make sure that we always have video memory available for our application, that other applications are not going to use up all the resources, and then we end up crashing and enter into a safety critical, dangerous scenario. So we needed very low-level control over the memory management of the system. We wanted to do very agile development workflows that would really benefit from having integrated tool commands. For example, on the screen here, you see that we have a debug window that's drawn inside the engine, which makes it really useful for doing development on a target board where you don't necessarily have a lot of computing resources or a network stack to be able to send performance data over a network for viewing on a separate terminal. It's all running on the same screen. Then it's very convenient for an agile developer. We realized very quickly that while commercial engines do give you a lot of capability in terms of what you can draw, that's actually not a good thing for safety critical flight software, because radiation upsets, they're called single event functional interrupts. When a radiation strike hits the program counter or some part of memory, it could corrupt memory, or it could move the program counter to a section of execution that you didn't expect. And if you have code that is untested because it was never used during development but was still shipped with your engine, you have potentially undefined behavior that could occur in your vehicle. So you want to remove all code that you don't expect to ever be executed. So really we found that capability for developing more secure software, being able to certify its use in a safety critical environment, being able to use all the latest technologies rated for safety criticality, like the Vulkan Safety Critical Graphics API, which was not even in existence at the time when we did our initial trade study. Having the flexibility to add that capability later really benefit from having our own engine. In addition, the only real features that we needed for our display was drawing text, lines, and images. And that gives you everything that you see on the screen in front of you. So we didn't necessarily need all the advanced features that you could get with a commercial engine. Overall, we decided to kind of restart our engine development with everything that we had learned, plus all the knowledge that we had gained in terms of UI development, to create the space technology application renderer, which was prioritized to be low power. We're talking about running on the same amount of power as maybe a decent calculator. Being relatively high performance. And when we say high performance, we're not talking about photorealistic graphics. We're talking about running at a solid 30 frames per second, given relatively constrained hardware. And we wanted a zero dependency graphics engine. That means that we're not relying upon any third-party open source software. We're solely relying on our own software, which normally you would think would be a detriment because you're not reusing old code. But the idea here is that if we write all of the code ourselves, we have full control over how everything works. It's relatively simple in terms of its overall scope, so it actually is pretty achievable with a small team. And you can mitigate supply chain risks from third-party developers. We then, as we did our implementation, we found that we were able to achieve a higher degree of agile development capability because we had implemented some unique features, like the ability to program in a non-scripting programming language like C, which is extremely high performance. But at the same time, we were able to recompile code while the engine was running without shutting it down. So that gives you the same kind of degree of flexibility you get with a scripting language, but all the performance and memory safety that you get with a non-scripting language. We also were able to do a lot of interesting prototyping capability for augmented reality using VR tracking technology. So you may know the HTC Vive VR headset, which has the outside-in tracking capability with the Lighthouse base stations. So we placed base stations in our laboratory environment to give us extremely accurate tracking capability in 6 degrees of freedom of space. And we essentially used virtual reality to simulate augmented reality. We would create an Unreal Engine, photorealistic terrain of the lunar environment. We would have the real, quote unquote, flight software for this augmented reality display. And we would project that image on top of the virtual lunar environment. So we were able to basically pretend we had a point tracking solution that doesn't actually exist in the real world yet, but would allow us to demonstrate and develop the capability of interfaces for when that point tracking solution does exist in the future. I think one of the things that really stifled our development early on is that we were too worried about what other people would think in terms of what we were capable of. We were thinking, it's going to be too heavy. The mechanical engineers are not going to let us do it because it's too heavy, or the thermal engineers aren't going to let us do it because it's too hot. Or the electrical engineers won't let us do it because it uses too much power. Or the command and data handling people wouldn't let us do it because the software would be too complicated to analyze. But we kind of realized that people didn't understand how good this technology can be for navigation, and until we actually show them what it's capable of, kind of creating a vision of what the future could look like and driving us towards that future, as opposed to kind of not knowing where the future is going to go and trying to force our way through the fog to get to an undefined solution. So overall, the engine development capability was pretty important for our project. I think we're ready to move on, Sarosh.
Okay, cool. Thank you.
Mm-hmm.
Okay, so now kind of walking through where the design ended up. So this is essentially what it looked like. And this is what we've used in various parts of field testing. And you'll notice this does look, again, very different from pedestrian displays because things are really different on the lunar surface and you need different things in order to navigate there. So we have phase elapsed time in the top right corner, and that's essentially like how long have you been on your EVA for? We've got a progress bar. So this is where were you are you going, and how far are you from where you're trying to get to? We've got a map, and this will probably look most familiar to you. It's got a live PNT data dot, a live heading cone. We've seen that in Google Maps. It's got a breadcrumb trail. This is really helpful because in testing, crew expressed the desire to go back to a place that they had already been. So having a live breadcrumb trail was super helpful for that. We also have a straight line traverse path. This isn't something you see in consumer navigation displays because we're never really trying to get from like point A to point B with a straight line. There's usually pathways and roads that we can follow. But for crew, this was super helpful because it provided them with a little more efficiency to get from point A to point B. Before having a straight line traverse path, generally they'd have to traverse even farther, potentially just to find like a crater or a hill or just something that they could use as a reference point. With this, they don't need like a physical reference point. They can just kind of walk there directly. We also have pin drops. So if a crew member sees a super cool rock and wants to look at it on their EVA the next day, it'll be a lot easier to recall where that was if you're able to drop a pin. We have registered AR. And this is kind of what we were waffling with a little bit. The ultimate goal would be to have registered and unregistered AR. So the top-down map on the right, as well as registered AR in your actual environment that you can walk towards. So again, think kind of like video game points that are pointing you a specific direction. Options for how to use the registered and unregistered augmented reality, and then just zooming in and out. It's really helpful when you get close to somewhere to be able to see all the details. And then also north up versus track up. This is particularly important on the moon, right? Because there's not really like a north, south, west, east grid coordinate system there that exists right now. And so being able to tell kind of like where you're facing and what you're looking at is really important. And so through a lot of testing, general trends have indicated that usually, as compared with a paper map, users will arrive more quickly at their destination. They're more accurately able to find exactly where they need to go. And I see that we are past the 30 minutes. I'm almost done. The path to the waypoint is more efficient. So this is still kind of along the same lines of you can take a straight line there instead of needing to like go find a crater or go find a hill to try to get to where you need to go. You're able to talk more about science and geology. So one thing we noticed from communication analyses is when you have, at least for us, a heads-up navigation display, you don't have to spend 20% of your time just trying to figure out where you are and where you're going. You're able to talk more about what you see around you. You're able to make more observations that you may not have noticed initially. And your mental workload decreases a ton because, again, you're not using 20% of your brain just trying to figure out where you're going. immediate imagery feedback is helpful. So again, right, I said it's kind of like a disposable camera, but worse with what crew has right now. So it was really, really helpful for them to just have in the corner of their eye overlaid onto their environment images of what they just took. It's also really helpful for comparing images. If you're at one place and you take a picture, you go somewhere else. Now you can see the picture that you took and compare it with where you are. You can see the difference in the types of rocks that are there to give back to scientists on Earth who will be able to tell you the history of that area of the planet. And then whatever controls exist have to be robust, easy to operate in a pressurized glove, and intuitive. So the controls that we used, that we developed over time, were 2 buttons and a dial. So really similar to just like a commercial mouse, but built with bigger buttons, built in a slightly different configuration. And we had a lot of different prototypes trying to figure out what the easiest way to control an augmented reality display would be. Oops. No. So this is my pretty much last slide on general lessons learned. So I'll start in kind of that first column, not operating within constraints. I think this was a huge thing that Matt really touched on, and it's that despite technological limitations or limitations that maybe we imposed on ourselves based on what we thought was possible, limited our ability to innovate. What really, really drove a good solution was basically ignoring those constraints, believing that they would work themselves out, and driving towards a vision of something that you wanted to see at the end of the day. The second is innovation is a mindset and an end goal. So throughout the entire time, we didn't lose that end vision. We were constantly driving forward that this was something new, driving forward that it was something different, and iterating on that. And then the last one in that first column is use case driven design. And I'm sure many of you probably know this, but it may seem obvious, but it's actually really hard to remember that you're driving your solution towards a use case. So when you think about what does the crew member need in order to work on Mars, what do they need to see to make a decision? Using that to drive your design is really important and sometimes does get lost in translation, which is why testing is super important. In the second column, we've got continuous development and adaptation. So working with, right, limitations in funding, limitations in timeline, limitations in technology, and just building your mock-up anyway, and then iterating on it with everyone in the same room, changing and rolling with the punches, and then also adjusting your priorities if it seems like your use case is changing or the priority for the use case is changing. The initial iteration of our design wasn't focused only on navigation. We learned through testing and analysis that navigation was taking up a huge portion of the astronauts' mental workload, and then we focused on that. So being flexible in that was really important. And then mocking up the ultimate vision. So it does not matter how low fidelity it is, it's still going to probably be extremely helpful to do. We had a ton of tabletops. We had a lot of really bad 3D prints. We had a lot of really good 3D prints, but making sure to keep that like ultimate, this is what we want it to look like on Mars is really important for our entire team. And then we have a fun little saying that I put on the slide. It's the inch pebbles together that become the milestone, right? So like you break up a mile into inches, break up a stone into pebbles, and then you slowly build those up. You eventually end up at the place that you want to be. And then I think you'll be getting a recording of this, or at least slides. These are some publicly available documentation and other products that our team has produced. If you have any other like questions or are curious about it, feel free to use those QR codes